Hello everyone, welcome back, and we're going to be doing another transport problem. In this case, today we have a tube with gas flowing up it, and the walls are wetted as liquid is flowing down. And we're going to be attempting to see the relationship between these three dimensionless units and this problem. In this case, we are looking to see if these are the appropriate dimensionless units in this case. So we have the Sherwood, Schmidt, and Reynolds number, which are dimensionless unit groups. So what we want to do is attempt to relate the equations in this problem to these three dimensionless groups using dimensional analysis and the Buckingham Pi method. So what we want to start with doing is we want to start by defining the variables that affect this problem. So we have gas flowing up the tube and liquid running down the walls. So at some point, the liquid is going to go into the gas and flow up. So we have some kind of mass transfer. So we know that this is going to involve Kc, or the mass transfer coefficient. We also know variables that will affect this problem are, let's say, velocity, density, and then viscosity of the fluid also, and then the mass diffusivity, so DAV, and finally we also know that the characteristic length, in this case it would be the diameter of this pipe that the gas and water are in, but there's always a characteristic length involved in these problems. So now that we know the variables from this problem, we need to define them in terms of the three base units. So those are mass, length, and time. So in this case, mass is going to be the kilogram, the length is going to be in meters, and time in seconds. So we need to first establish what variables units these variables have. So starting with the mass transfer coefficient, or Kc, the units for that is kilograms are not involved, so that mass is not involved in, which is weird. Mass is not involved in mass transfer coefficient, but it's true. And it's meters per second. Velocity is the same, so I'm just putting 0 because it does not have a kilogram in it. However, the meters are on top and the seconds are on the bottom, so that's what it means when it's 1 and -1. Density is a mass over volume. In this case, it would be the kilogram over meters cubed. So that'd be a -3 since it's to the third power, and it does not involve time. Then we're on to viscosity, and viscosity is a kilogram per meter second. Mass diffusivity is mass over an area. So in this case, it would be kilogram over meter squared. And then we're going to finish up with, I did that wrong. That's not what it is. I think it should be, I got that wrong. It's area over time. My bad. So the diffusivity is an area, so meter squared over a second, how fast it's diffusing, and then we have the characteristic length, which would be 1 meter section. So now that we have the units for these variables defined, we need to make a dimensional matrix out of these. So essentially we're just doing this, putting brackets around that, and we'll call that a matrix. So this is our dimensional matrix. So now that we have our dimensional matrix with our 6 dimensions in it from this problem, we need to identify the rank of a matrix, because we know that the number of variables, we'll say n minus the rank of a matrix, is equal to I, where I is the number of dimensionless units or dimensionless groups that this problem will have. So in this case, we have 6. We have 6 variables, and our rank is undetermined for right now. It equals the number of dimensionless groups. So now I will hop into Python and show you guys how to use Python to easily calculate the rank of a matrix without going into the nasty linear algebra by hand. So when we're trying to understand the rank of a matrix and find out how many dimensionless groups we have, we need to subtract the number or the rank of these matrix from the number of variables we have. So when we're trying to determine the rank of a matrix, we need to use linear algebra, and the linear algebra catalog is in NumPy. So like most times, we're going to start by importing numerical Python as NP, shift enter that, and then we're simply just going to, like I said, it's linear algebra in order to determine the rank of a matrix. So we're going to say, first we need to define our matrix, so I'm just going to call it matrix, and say that our matrix is equal to, and then we need to recreate that matrix of powers that we had before. So I have that already made up, so I don't have to type it out. But these are just the same numbers that we worked out before. So these numbers just represent the powers in terms of kilograms, meters, and seconds of those variables, of those 6 variables that we have. And then we need to go into and say the linear algebra. So NP from the numerical Python, we're going to go into the linear algebra catalog, and we're going to, it's a matrix, and then we're going to find the rank of that matrix, and then our variable is called matrix. So let's shift enter. So that gives us 3. So now we know that the rank of our matrix is 3. And so now we can go back and we'll find that number of variables, 6 minus the rank of this matrix 3, 6 minus 3 is 3. So we should have 3 dimensionless units coming out of this, but we'll go ahead and head back. Now that we know the rank of our matrix is 3, we can say R is 3, and that would make I equal to, so we know that there are 3 dimensionless groups that are associated with this problem. So now that we know how many dimensionless groups we have, the next thing to do would be to write out these dimensionless groups. So we use pi1, pi2, and pi3. I think I can fit them all in here. Okay. So for each of these dimensionless groups, we need to establish a core group of variables that are going to be constant throughout all 3 of these dimensionless groups. The only rule for this core group of variables is that they need to contain at least 1 in each of these categories. So for example, you couldn't pick mass transfer coefficient, velocity, and diffusivity because they are all missing a kilogram. Other than that, there are no strict rules as to what variables you pick for this core group. But in this case, we're going to pick the core group of we're going to say our core group is, and then we're going to say it's the diffusivity, this diffusivity density, and we're also going to say that the last one is the the characteristic length, or D. And then we're going to alter this last one with the other 3. So our core group is DAB, the diffusivity, our density, and our characteristic length, D. So that is going to be consistent throughout all 3 of these dimensionless groups, and they're all going to be raised to some power. And then we're going to be altering or changing the remaining 3 variables in for each of the groups. So we'll say that pi1 is, let's go, DAB raised to some power A, density raised to some power B, characteristic length some power C, and we're going to say, let's start with KC. And then similarly, we're just going to keep the same core group, but now it's AB some power D. I don't think I'll be able to fit all 3 of these in here. I'm going to keep, once again, and then we're going to say, let's say velocity for this one, and then the last one we're going to change out is the viscosity. So like I mentioned before, the core group stays consistent throughout. The power that they're all raised to is changing depending on what the units need to be. And these are creating dimensionless groups, so these variables need to cancel out. And that's why they're raised to certain powers to allow them to cancel out. So we need to find out what A, B, and C are for pi 1, D, E, and F, and then G, H, and I for their respective dimensionless groups. So if we take a closer look at the units again for each of these, we know diffusivity is meters per second, or meters squared per second, area per time. So we have meters squared per second here. Raised to the 8th power. Then we have density, which would be kilograms per cubic meter. B, and then characteristic length is just meters raised to the C, and then the mass transfer coefficient is meters per second, and that is not raised to any power. So like I said, these need to be dimensionless groups. So we need to get these to cancel out with the meters per second, which is the mass transfer coefficient. So you can do this one of two ways. You can start creating a system of equations, which is hard, but only gets you the answer, or you can kind of just look at it and be able to use deductive reasoning to start finding it, which is nice on ones that might be simple, because if you look at this one, I can already see that B is going to be 0 because we need these three, the core group variables, to be the opposite of the meters per second. So we're going to need to end up with units of seconds over meters, and that doesn't involve any kilograms. So right off the bat, we can say that B is going to be equal to 0 because that gets rid of our kilogram component. So now you're looking and you're saying, well, we only have one other term that has an S in it, and that's going to be our diffusivity. So we know that A is going to be -1. It has to be -1 because we need seconds to be on top, and we need only 1 second to cancel out with the seconds from our KC. So we know A is going to be equal to -1. And then from there, we can figure it out. The only unit we have left is meters, and to cancel meters out, we would, so as A is -1, we'd flip that. So, and B is 0, so this meters cubed is not in here anymore. So we have meters squared on the bottom, and we have a meter there. So we end up with 1 meter on the bottom, which is exactly what we need. So C would just remain constant, remain the same, and it would just be 1. So now we know A, B, and C. We are going to put those in for this equation and say, now room here. I didn't put a large enough whiteboard. We know A is -1, B is 0, and that. So now we put them in this equation. So A is -1, so we know dimensionless group 1 is diffusivity on bottom. The B was 0, so we don't have anything for density, and then the characteristic length was 1, so that just stays on top, and KC stays on top. So if we look at dimensionless group 1, we can see that it's the same as the Sherwood number. So dimensionless group 1 is the Sherwood number. So that is our first dimensionless group. if we take a look at so if we look at dimensionless group 2, this is what's really nice about picking this core group. We see that the velocity has the same units as the mass transfer coefficient. So the only real change, we'd go through the exact same math, and we would just come up with a velocity instead of a mass transfer coefficient. So we know that the second characteristic group is going to be the velocity times the characteristic length over the diffusivity. Like I said, that doesn't happen every single time. It's just because the core group we picked this time allows for that to happen. So I erased 23 so I could get more room. But dimensionless group 3 is going to be the same core group again, the diffusivity, raised to the G, the density raised to the H, and the characteristic length to the I, and then the viscosity is the last one. So we're going to go ahead and write down the units again. Meters squared per second for diffusivity, kilograms per meter cubed for density, just meters for characteristic length, and viscosity is a kilogram per meter second. So this is what I'm talking about. Now it's getting a little bit harder to determine what we need to do. To be fair, we can see H is going to be 1, or H is going to be -1 because there's 1 kilogram in the equation, and we need to cancel out. Remember that they're dimensionless groups, so at the end of the day, there should be no dimensions in these. So if our changing variable, in this case is viscosity, has a kilogram on top, that means this kilogram, the only other kilogram in the problem is from our density variable, so it needs to go to the bottom. Therefore, H is -1. So now that we know that H is -1, we can go to G, because G has seconds, and it's the only other variable with seconds in it this time, and they both have seconds on the bottom, so we know that G is going to have to be -1 as well, because that flips the second up to the top and will cancel out with our seconds in the bottom from our viscosity term. And then we need to find I, and just like in dimensionless groups 1 and 2, meters is the last variable to be canceled out. So if we plug in -1 for H and G, we'll get I is equal to, let me see here, H there, you get a meters cubed on top, and we're looking for the opposite of this, again, the viscosity term, so we're looking for what value of I puts only 1 meter on top. So we have 3 go to the top from there, and 2 go to the bottom there, so we have 1 on top, which is exactly what we need. So I should be 0. So our last dimensionless group, I3, should be the viscosity over the density times the diffusivity. From there, those variables right there. So now if we look back up, like I said, the first dimensionless group was the Sherwood number, which is the Kc times the characteristic length over the diffusivity, and then we have dimensionless group 2, which is actually known as the Hecklet number, and then we have dimensionless group 3, which is called the Schmidt number. So now that we know all these numbers, we're missing one term because we want this in relation to the Sherwood, Schmidt, and Reynolds number, and we don't. We have the Sherwood, Schmidt, and Hecklet number. But if you look at the units of the Reynolds number, we can see that the relationship between the Reynolds number is the quotient, or it'll be the second dimensionless group over the third, because the diffusivities will cancel out and you're left with the units of the Reynolds number. So if we look at that, we do pi 2 divided by pi 3. Yeah. Once again, not a big enough whiteboard. Pi 2 over pi 3, which is the Peclet number over the Schmidt number, we get the velocity, characteristic length, diffusivity over the viscosity, density, once again, diffusivity. So the diffusivities cancel out, and then you're left with the density goes to the top, velocity, characteristic length stay on the top, and you're left with viscosity on the bottom. Which is, if we look up here, is our Reynolds number. So now that we've found the three dimensionless groups that represent this problem, we have dimensionless group 1, which is the Sherwood number. We have dimensionless group 2, which is the Peclet number, and dimensionless group 3, which is the Schmidt number. And then we found that the relationship between the Peclet number and the Schmidt number gives us the Reynolds number. Now we can look forward to the second part of this, which is coding out why this relationship works. And it's an exponential relationship between these three dimensionless groups. In this case, it's the Sherwood number is equal to, and then we have the coefficient, and then we have the Reynolds number raised to some power to be determined by experimentation, times the Schmidt number raised to some power c. So this is the relationship we're going to be taking a closer look at in the coding section.